Hey kiddos, today we're going to do slope fields, and they look pretty strange, but they're not so bad. So let me walk you through what you're doing before we do it. So that's the curve y equals x squared. Back in September, we talked about drawing tangent lines to curves. So if I went here, the tangent line would look like that, but if I went here, it would look like that, but if I went here, it looks like this, because it changes depending on where you are on the curve. As different points are going to have different slopes, even though that looks awfully linear, because whatever. So today's purpose is, if I take away the curve and I only have this sketch of tangent slopes, of tangent slope line segments, could I figure out what the curve looks like? So for this one, yes, because I only drew it in one place. But if we're talking about the fact that this slope is 2x, then this could have been x squared plus 7 or minus 3. It could have been anywhere. So these same line segments can exist down here, can exist up here, like they can exist all over the place. So these things end up looking pretty messy. So let's walk through a question, and we'll talk about why we do them as we go. So I'm given a differential equation. Oh, by the way, this is called slope field paper. There's grid paper. There's extra blank grids in Canvas if you want to print and download. I don't think you need them for your homework, but if you want them to help you take notes, that's fine. Because I think we're going to do 2, maybe 3. We'll see how excited we get here. All right, first thing we're going to do is we're going to sketch the slope field. All right, so the slope field for this differential equation, the slopes of this differential equation are y squared, which means at any point, the slope at that point is equal to its y value squared. So for example, if I'm at the point 0, 0, my slope there would be 0 squared, which is 0. So I go to 0, 0, and I sketch a slope of 0. If I'm at the point 0, 1, my slope there would be 1 squared, which is 1. So if I go to the point 0, 1 and I try to sketch a slope of 1, it would look like this. I'm not drawing entire lines. I'm just kind of eyeballing. If I go up 1 over 1, then I have a slope of 1. So you're just drawing little tangent line segments at every dot. So if I go to 0, 2, same thing. 2 squared would be 4. So all the way up here, I have to eyeball a slope of 4. That's pretty steep. Now, nobody's going to get a ruler out to make sure it's perfect, but a slope of 4 better look steeper than a slope of 1, and a slope of 0 better be flat, and negative slopes better be decreasing. Just as long as you have a general direction, you're going to be fine. I've never seen them ask you to actually sketch a slope field by hand on the AP test, but I think it's good for you to do the first couple times. So you can sit here and plot points all day long, and maybe you have nothing better to do than to plot points all day long. But we can use patterns to help this go faster, because eventually I'm going to figure out that all of my slopes are only dependent on the y value. So as long as I'm along this line, y equals 0, I'm going to have a slope of 0. So all of these have horizontal tangent segments. And then if I'm up here at y equals 1, all of these are going to have slopes of 1. So that can make things go a whole lot faster. Plugging in points always works. Always works. But sometimes it's not your quickest option. All right, so I am going to fill out a lot of this, but I'm going to fast forward you to when I already have it filled out. All right, here's enough of a slope field filled out that I can get a good sense of what's going on. So the next thing we're going to do with it is we're going to sketch something called a solution curve. And like I talked about at the beginning, the solution curve is probably going to look similar anywhere you start, but you need a starting point. So we're going to draw a solution curve that goes through the point 0, 1, which means I have to hit this dot at 0, 1, and then I want the curve that goes through there. Now, I don't need to hit any other point exactly. I just need a general shape. So if I move to the right of this point and I come off of this point moving to the right, I'm going to come off of this point with a slope of 1. But the second I'm off that slope of 1, that point, my slope changes. So I know that by the time I hit this line, I better have a slope of 4. But in between there, I've got slopes of 2 and 3 and 1.5 and 2.2 and everything leading up to 4. So I have to be continuously increasing at an increasing rate until I hit here. Now notice that I'm not really trying to hit a point exactly, but I am trying to make it look parallel all the way across. So I think that's going to keep happening. And then I got the pattern. These guys are going to have slopes of 9. These guys are going to have slopes of 16. So this thing is really increasing quickly. And now when I go to the left, I'm going to do the same thing. I'm going to leave the dot with a slope of 1. And now my slopes are getting less positive, and they're approaching 0. And what's going to happen is I'm going to hit this line that has a slope of 0 all the way across, and I'm going to get stuck there because slopes of 0 mean I'm completely horizontal and we're not increasing or decreasing at all. So I'm going to hit that line and get stuck. And that's what a general shape of that solution curve would look like. Now, because I gave you this one that I gave you, let's go solve the differential equation and see if our curve looks like what we think it should look like. So right now I have all these little tangent slopes for my differential equation. And I drew what I think the actual solution, like I think this is y equals something. I think this is the curve. Let's go solve for y equals. So if you remember how to solve a differential equation, we are going to separate and integrate. So I will separate. I'm going to call this, well, what do you want? You want it underneath probably. So let me rearrange. So this is y dy over y squared equals dx. When I integrate, think of this as y to the negative 2. So when I integrate both sides, I add 1 and divide by the new, I get negative 1 over y equals x plus c. I'm going to go ahead and plug in this initial value of 0, 1 so I can solve for c. So negative 1 over 1 equals 0 plus c. So c equals negative 1. So now I've got negative 1 over y equals x minus 1. I'm going to negate both sides. Oops, that's a 1. So I'll just switch it 1 minus x. Now I'm going to reciprocate both sides and flip it upside down. 1, stop it. Okay, so that's what algebraically the answer should be. The answer should be this rational curve that got shifted 1 and reflected, if you remember anything about graphing, transformations of functions. So does this look like a rational curve? Yeah, looks pretty good. Did it get shifted 1? That's not super great to see. Like the asymptote is actually here, but my sketch has it more over here. That's okay. We're human, not a big deal. All that means is that when I was eyeballing, I didn't have this increasing fast enough, and it really should have done that. Okay, nobody's going to jail over that. So this is a graphical approximation to this actual answer. Okay, it's a graphical approximation to an actual algebraic answer. We're going to do one more thing with it. We're going to go find, where's my curve? We're going to go find the second derivative. Okay, so if I differentiate both sides of this equation, I'm going to pull a power and subtract 1, but then I have to take the derivative of what's inside, and what's inside is y, so it's times dy dx. There's a chain rule there. Okay, so the second derivative is 2y times dy dx, remember, is y squared. So I just put that back in. So this is 2y cubed is our second derivative. And if I analyze our second derivative, let's do it at the 0.01 again. So let's see, y is 1. I'm going to get 2 times 1 cubed is 2. what I'm looking for is the sign. That's positive. The fact that that's positive, remember what a second derivative tells you about the original function? Second derivative talks about concavity of original functions. So the fact that this is positive means that y is concave up at the point 0, 1. So let's check our curve. Yep, our curve is concave up at the point 0, 1. So that also feels good. All right, here's the reason we have slope fields. The reason we even ever talk about slope fields is for questions like something like this. If I gave you dy dx equals x minus y. So I can sketch a slope field for this. I could sit there and plug in points all day long and do the x value minus the y value and plot that. And then I can approximate a solution curve. What I can't do is separate and integrate this one. So because I can't separate and integrate, I can't find an actual algebraic answer, I have to rely on approximations. So that's why we do slope fields. Remember, the only differential equations you guys can solve are separate and integrate ones. All right, so again, I'm going to just magic pop an answer up here. If you want to draw yourself a slope field, go for it. I'm not even going to talk through. And then we're going to draw a solution curve for this one that goes through the point through, I don't know, 1, -2. Actually, I'm going to do 2, and then another one through 0, 0, because these look different. So I lied a little bit. Let me tell you how I can make this go quick. Pick your favorite slope. I pick 0. Set it equal to your differential equation and rearrange. So I'm going to have slopes of 0 along the line y equals x. All right, well, I took Algebra 1 once. Here's the line y equals x. All of these dots need to have horizontal tangent segments. It messes with your brain because I know you want to give them slopes of 1 because you just graphed a line with a slope of 1. I know. And then we do it again. So if I want slopes of 1, and I set that equal, and I rearrange, I get x minus 1. Well, that is this line. So I'm going to graph slopes of tangent segments of 1 along that line. And I can continue that throughout. Okay, so now pause, and you keep going. All right, there's a very rough sketch. If I do a solution curve through 0, 0, I got to hit here. As I come off of this point, I'm going to have a slope of 0, but I only have a slope of 0 when I'm sitting along this line. So the second I leave 0, 0, I don't have a slope of 0 anymore. What's going to happen this time is we're going to get stuck along this slope of 1 because I'm going to hit a slope of 1 and stay a slope of 1 because I'm sitting on the line with a slope of 1. If I move the other direction, I'm going to hit a slope of 0, and then I'm going to hit -1 and -2 and -3, and they're just going to be more negative. If I go through 1, -2, which puts me here, the same thing's going to happen eventually. So this one, these start more steep and kind of level out, but I'm going to get stuck here again. And then this side takes me this way. So this is an example where a slope field, different starting points can give you different shapes of curves. All right, most often you see these in multiple choice questions where they give you a slope field and say, what's the differential equation? So just some things to pay attention to. I immediately see a slope of 0 here. So this is where dy dx equals 0. And this is along the line y equals -1. So when y equals -1, every time y equals -1, I'm going to have slopes of 0. That's going to be important. I also notice that this side of my graph, when x is greater than 0, it has slopes that are positive. Some are more positive than others, but that matters. Same thing here, but same but opposite. dy dx is negative. And then I also notice these slopes. So at x equals 0, the line x equals 0, I have undefined slopes because they're vertical. So I just try to find those general patterns and I use them in my multiple choice. So if x equals 0 has to give me undefined slopes, I know the answer is already circled because I had to check it before I press submit. Then if x equals 0 gives undefined, then I'm immediately eliminating this answer choice because x equals 0 would give slopes of 0. If y equals -1 gives slopes of 0, then any of these are still fair game because they give you a 0 in the numerator. So the next thing I'm looking at is, do you notice that, like, for example, this is squared and this is squared, which would make this always positive. Oh, but look, there's a negative. So this one is always negative. Well, that can't be my answer choice because I have some positive slopes. So I'm down to these two. This one has my y values always positive. This one has my x values always positive. But what I wrote here is that the sign of my slope is dependent on the sign of x. So that's why I picked here. Now, friends, if you can eliminate two of these things, or even one, it's only going to take maybe 1 or 2 points. You can literally sit here and plug in a point. Pick the point, 1, 0, plug it in, see if you get a positive answer. And that's okay to do. You just don't want to have to do that for 4 answer choices if you can help it. All right, friends, that was a long video. Sorry in advance. Let me know if you need anything.